Hello everyone, welcome. This is the IEEE at Home blockchain series. We will be having with us another episode, and today we'll be having the topic traceability for industrial environments based on a high tamper proof system enabled by blockchain technology. With us we have a team, and the lead of the team for this presentation will be Miguel Teixeira. Miguel has graduated in electrical engineering at the University of Trás-os-Montes e Alto Douro, has a post-graduation in information management obtained at the engineering faculty of University of Porto, and advanced training in business intelligence at University Portugalense. He has started his professional career in 1995 and has known several IT and management roles at different companies and several industry sectors, such as consultancy, textile, food, metals, and automotive in Portugal and France. He was awarded CIO of the Year Portugal 2019, Business to Business category, and Most Inspirational European Digital Leader of the Year 2020 by Sionet International. He maintains the role of digital lead for powertrain plants at Renault Group, and he is a PhD student at University of Aveiro, working under blockchain and IoT subjects for industrial environments. So, Miguel, you have the screen sharing, not the floor, okay? You can start.
Okay. Good afternoon. Thank you very much for the excellent presentation, and thank you very much for the opportunity to share our work and the opportunity to have a contribute for the blockchain community. So I will present on behalf of a team our subject, as you said, traceability for industrial environment based on high tamper proof system enabled by blockchain technology. So this subject has come to us about the use case needed for on our industry, that the objective is to give trust and transparency on the value chain on our automotive sector. Let me change this. So as I said, I represent a team. The team is composed by Diogo Costa, is a Master of Science in Mechanical Engineering and a PhD student at University of Aveiro. It is with us. Also Guilherme Salgueiro, that cannot be with us, but he participated on this work, is a Master of Science in Mechanical Engineering, also University of Aveiro. And two professors, Armando Nolasco Pinto and José Paulo Santos, both PhDs and professors and supervisors of this subject, also at University of Aveiro. We had an additional collaboration of Telmo Monteiro from University of Aveiro, mainly on our testing phase. So I will go to these subjects. I'll present the global context and the problems to address as we saw it on the automotive sector. Some brief overview about the technology, our proposed approach and the architecture we chose for our work, some prototyping that we implemented with the team, some security considerations already done, and the testing that we implemented, the next steps, and some key innovation topics. So now, as consumers have new behaviors, they are demanding more transparency and more trust about the products they buy. So they are asking to understand how the products were made, what was the process used to use it in the products, and what was the traceability of the products they are buying. So for now, what we consider in our value chain, we have some slow access to information, and sometimes it doesn't exist, this information, as it coexists on several systems. So the connectivity is also very complex, and as we work also with many systems our system, our client systems, and our providers and supplier systems. So we need to assure that all the value chain from inbound logistics to service have a correct traceability of our products. So as I said, we have multiple systems and multiple databases, and we have many stakeholders and many entities involved. So the goal was to give trust and traceability of the products and the process and even the machines, to address a suitable architecture, to address security and privacy concerns for all, and to balance this with efficient and reliable information. So, as we said, to address this problem or this use case, we thought about to use a decentralized architecture based on blockchain. So, blockchain can give us a framework, if I can say like that, or a network implementation that give us some immutability on the transactions we implement in our systems and in our value chain. Entities must have a consensus protocol and agreed of the rules to implement this network. It's kind of if I can say like that, a democratic system to assure that information is not tampered. So the entities and the nodes involved on this network agreed on some rules and assure that information is correct. And nowadays, traditional databases have information on one database and could be tampered. And this, between quotes, democratic system allow us to give more trust and immutability on the transactions we implement. So in this network, as I'm not going into deep blockchain analysis, you are all experts on that. We analyzed the protocols used on the blockchain networks and several distributions that exists, and we choose to implement from scratch a network. And this network is based on the implementation on the nodes, and the miner or the node that will be elected to assure a transaction on the network. It's based on the protocol based on the proof of authority, and the last node that implemented the transaction, which will be the first to assure to assure a transaction on the network. This means that there's no competition based on effort or something like that, because every node adds the same opportunity to assure a transaction on the network. The last one to mine a transaction, it will be the first to mine, and it goes on loop like that. So our proposed architecture based on these concepts of immutable and security kept of data, high throughput and swift data access, and a lightweight and modular framework. As you will see, we'll keep on blockchain not all the registries about our process and machines, because this kind of information of traceability will be kept on enterprise systems. What we will keep on our blockchain is only the hashed values to certify that we will certify by checking these hash values with the enterprise systems. We will keep for lightweight approach only on the blockchain the hashes from used on the transaction. So our architecture is based on this, and it consists of a layer of intelligent data acquisition that is coming from different machines or different sensors. And then on top of that, we'll implement a core trust network based on the blockchain that will communicate with the enterprise systems and gives the inputs necessary for HMIs, for the visualization from different clients, if they were external or internal, and a model that consists of a control cockpit to monitor all the network, to monitor the transactions, to assure the rules are implemented. So as on the right side, modular architecture, it will be implemented security by design. It should be responsive. We prefer that intelligence goes on the first layers on the edge. So the most we can assure at the edge, the better. Transversal control models, responsible compatibility with existing systems. That means we use standards as APIs to communicate with these different systems, and we will need to respect the business rules and the data access limitations. So, as you can see, this concept will be implemented on several units. As you can see, on the first basic unit will be a business unit from a plant. As you can see, I don't know if you can see my mouse. There is a line, assembly line here on a plant, and several business unit consists of a plant. Plant will be connected to this network, and we can connect several plants with several business units and give visualization to the clients, the suppliers, the internal entities, and all stakeholders involved on the value chain. And to assure that, we want that this architecture to be scalable and open for future development. The concept was thought about taking this big picture into account. In our prototype, as you will see, we will analyze a business unit, but it is extensible to a plant or another business units and connectivity between the plants. So this is a use case based on a Renault scenario. So I can give you some brief information. What is a business unit in our case? Here you can see an assembly line and a machining line. We chose this scenario because it is complex. It has some automatic operations and some manual operations, and it has a good diversity and has several parameters involved. So this gives us a good scenario of representative of what is a shop floor on our automotive sector. You have one assembly line, semi-automatic, one assembly line, full automatic, as you can represent it with several operations. And we have here some machining area with some Uran machines, one type of machines, and another Grob machines, another type of machines. So this is a heterogeneous scenario that can give us inputs to have some testing and to test all the hypotheses using our blockchain network. On the top of this, here you can have the traceability of our products. We use oil pump as an example, and we need to have some traceability about this product. And also, as you can see, there are several components that are assembled to constitute the oil pump, and we have some process information needed to assure this. So we have machine, you have process, you have product in our scenario. Our architecture based on blockchain, it's based on 3 layers. The first layer, it will be this, what we call some digital twins or sensing the field, collecting data from machines that then are interfaced with a gateway to collect the sensors from different areas. So they consist on a business unit that could be from a distance from other business units. So we have gateways at this level to interface several sensors. And then this business unit from 1 to N will be interfaced with enterprise systems for all the traceability, product, process, localization, whatever the assets are, and they communicate to the blockchain network. This is the second layer. And this blockchain, we have nodes. Nodes can be an entity at the maintenance department, an entity of the production department, an entity on our supplier, or an entity outside of our enterprise network. So nodes can be, and in our prototype, you used a scenario with a minimum of 3 nodes. And the database will be on each node, as we already know. Blockchain, it's one node, one database. The database that we'll use, you will see after, it's a MongoDB, and what we will store for lightweight purposes, it will be only the hashes, and these hashes with a timestamp will be checked with the information that will be stored on enterprise systems. So the system will check the hashes to assure that information is correct, is not tampered. And then the upper layer, the public HMIs and the private HMIs, that composes the user layer to assess all the system. And on the left side, we have the control models that will control communication, transactions, network rules, and other issues to monitor all the network. It will be the edge manager that interfaces with a model for dynamic routing manager, the blockchain network manager, and to implement security rules as cryptography and hashing and other functions associated with security. So as a resume, address different users by integrating profile management, communicating with existing systems using web services as standards, maintain only relevant data on the trusted decentralized network, only the hashes for lightweight purposes, management control models by function, as we can see here, and intelligent data capture at this level. So for prototyping, we implemented as the figure shows. So we used Raspberries and Arduino's models, and we used ASPs to act as sensors, and we communicate with the core trust network, the blockchain, using HTTP, and we will implement the security HTTPS. For enterprise systems, we use the ISA 95. We'll communicate between these models using web services such as microservices or APIs. And the visualization, we will use Java, HTML5, and other standards responsive web tools. For the control cockpit, we will implement OpenSSL using RFC 5246, HTTPS and TLS associated 1.3 associated with this. And I believe that it's clear, I hope. For the user layer, as we said, we will implement some rules and some rights. So public HMIs will give access for external users, suppliers, partners, or even the final consumer. So we need to assess only the required data for reading purposes, and some private HMIs for in-house users such as maintenance department, production department, to assure that real-time information and consult the system and other process purposes not needed to share with public users. Our blockchain and storage layer, we have here some demonstration how to implement the transactions. We'll have a block header. We have the transactions, what information that will be stored, and the minimum information that we will need to store: business unit ID, the capture, the sensor ID, the part ID or reference, the sensor data that was read, timestamp, and the data collection. This will be on the NoSQL database, and we use it MongoDB. So from sorry, it is in Portuguese, but I believe that is no problem. We have the ASPs represented as light LDRs. For example, the refresh rate that will have the reading from each ASP model. Then it will be sent for the gateways. and these then are stored on a temporary database, so we can then send this for the blockchain. And it repeats from other business units, as you can see here. For prototyping the HMIs, you have an example of a web-based HMIs representation here. As a global cockpit, we will have access to architecture map, visualization, the control cockpit, the core trust network, and all enterprise systems, and the layer of intelligent data acquisition. For analysis and queries, as you can see here, and is the example, we have nodes, blocks, the IDs, the gateways, the sensors, the hash values, and the part IDs. So we will have also a menu configuration administrator, so we can configure the system and all the entities, all the parameters necessary so to keep the network working. Here are some examples of the prototyping. So how to manage block nodes, to add nodes, remove nodes, clear nodes. Also the gateways, the same administrative tasks we can have for the blockchain. Some examples how to query the blockchain. We can query by hash value, by part ID, business unit, or even the block number. And also we can search these values and the results, typical results we will have in our prototype. It will be like this one. This is a query result example. The payload, you can see the sensors 01 and the reading of 20, for example, and the part ID and the timestamp associated. Renault business unit 001 give us the gateway, for example. So another security features we implemented also at the login level. So we limited one login, one session per second. User information is kept in a secure database only in hash value, as we said, and we implement TLS 1.3 in communications outside the networks, and AES 255 on both sides. Here an example of these implementations, and later the work this last year was to and I believe this is an important extensible point, is the fact that for the security, and we will test all the options in balance with efficiency and latency, the fact that we can choose the type of security as AES, or even to implement communication without encryption. And the generation of some keys or random numbers using physical generators based on temperature, pressure, and other hardware variables. Also, quantum generators we can use here, or generators on the sensor or the ASP. We can choose this and then apply, and then we see what is the behavior of our network. So another example how to deal with that. As you can see, how do we encrypt at the gateway level? We use a script that we used the keys to encrypt information, and we keep it on the temporary storage, and this temporary storage we then send for the blockchain. AES cipher block, as you can see, what we used, that the information is from block to block will be used on the next iteration. Also, some examples of the test we implemented. We test the entropy of the random sources used for this encryption, and we tested on ASP8265. We use it on the Raspberry, and we use random generated using quantum sources also. And the example, as we can see here, the average entropy will be, you can see it is on the ASP is 1, on the Raspberry is 7. It is closely, as we work with 8-bit, it is close of the maximum. Some tests that also we implemented, as you can see here, the response time using a 3-node approach and a 20-node approach. As you can see, as a Pareto of the time requests, we can see with 3 nodes we have delay time, a waiting time, and with 20 nodes we have this kind of response. This means that we should take into consideration the security issues together in balance with the efficiency and the latency that we need for our network. Also, some testing we implemented on the nodes and request time considering the nodes we implement on our network. This is by block number, this is by part ID. Also here we have a check we did with Wireshark to ensure that the information is encrypted. We can see here, and we can see here, and also we can see on this side. Also at the gateway level, we tested real-time encryption. We compared it on post-process encryption. We compared the values, it will almost the same. So we can do it on real-time, or we can do it on post-process encryption. So the entropy is similar, as we can see, but we should analyze and see what encryption we could choose at the edge level till the gateway. What is the best suitable? So the next steps will be the full prototype ready. It is not yet done because we need to assure that many business units, different networks, assure to implement the prototyping using the information on different networks and also on different plants. So for this year, we will implement with the help of the mechanical teams of Universidade de Aveiro some digital twins for the objects. We will represent a plant object, a business unit object, a gateway object, a node object, and we represent and simulate the behavior using these digital twins. These digital twins, if I can show, it will be similar what is here. So we will have business unit, we have sensors, we have plants, we have representations of a client and things like, and assets like that. And then the next step, it will be also to study the efficiency and latency, and we will balance with the studies done with security, and also use the quantum generated with direct interface connected. For now, we do it on a manual step, but what we want to, when the administrator selects a quantum generator random number, it will be direct interfaced with a quantum generator. Key innovation topics, so the ability to select suitable cryptography primitives as we saw, the use of quantum technology for enhanced security, and also to increase speed. Quantum could be used also on key generation, but also on distribution. And the modular architecture with multiple entities using API-driven development with blockchain. We believe in this concept and this framework, it's an innovative approach. So I go through this scenario. So to implement this at this level, we believe it will be an innovation for our systems. We have some MOS already implemented, but not using blockchain and not using full API and modular approach for now, but the people are working on that. So thank you very much for listening for this exposition, and also I would like to readdress the project team, because this is no one-man work. It's a work about many people. Thank you very much.